Thank you for inviting me. So today I'm going to talk about one problem called the K-cup problem. This is a joint work with Anupam Gupta and Jason Lin from CMU. So let me just dive into the problem. Okay. So this problem is a very simple problem. So given a graph G, possibly weighted, and an integer K, so this problem wants to delete the minimum weight edges, so edges of minimum total weight, to cut or partition graph into K connected pieces. Okay? So a very simple problem. Often, we're going to focus on weighted case, but we can talk about the weighted case here. So this is a problem, and then we want to design an efficient algorithm for this problem. Okay? And then depending on what kind of running time we allow, so there are like three regimes of this problem. So in the first regime, is when K is a purely constant. Okay? So we allow algorithms to run in time n to the any function of K, because since K is a fixed. Okay? So second parameter is more like new research direction in the community. It's called when K is a parameter, in a sense that the algorithms can run in time any function of K, some computable function of K, times a polynomial in n. Here, like big O of 1 doesn't depend on K. Okay? And then third regime, which is most restrictive, says that we often say that K is a part of input. I don't know why, but it says that so algorithm should be purely polynomial. Okay? So it has to be polynomial in both n and K. Okay? In this case, K is at most n, so actually we can say that it's a polynomial in n. Okay? So and then so one thing about big O policy. So I will try to be careful if I choose big O, because sometimes the K is a constant or sometimes not. So I will try to hide only absolute constants in big O notation, except possibly when we talk about n to the K, because if n to the K is already there, then some function of K is very small compared to this guy. So, but this is one big O policy here. Here's what we already knew in these three regimes. Okay? So even if when K is constant, it was not entirely obvious to get exact optimization algorithm. And then it was first done by Hochbaum and Goldschmidt in '88. So the first running time for exact algorithm was n to the K square. And then after a series of work, it was improved to the n to the 2K. And then when K is a parameter, then we knew that we could not solve this problem exactly, but nothing special, nothing approximation algorithm was known in that regime. And then in the most restrictive regime, when K is part of input, Saran and Vajrani proved that we can get two approximation. And very recently, assuming some complexity conjecture, so this two approximation algorithm was proved to be tight. Okay? So is everyone comfortable with this two approximation, the notion of approximation algorithms? Okay, good.
So when you say cannot solve exactly, that means
there's no exact algorithm. Sorry, second.
You're saying you reduce to W hardness?
It says that. So we reduce from K click. So this was a regime, and then this is a table. Okay. So in the first column, the first row, so we consider the regime when K is constant. Okay. So here, we know we can solve the problem exactly. So we are trying to optimize the running time of the algorithm. And then for the next two rows, we know that we cannot solve the problem exactly. So we try to optimize the approximation factor. And then this is what we knew. And then what I'm going to talk about today is my recent work based on three papers. That improved two things, or three things. So first, if you look at the second row, we kind of improve the approximation factor from 2 to 1 point something. So first paper gave 1.9999, and then second paper improved it to 1.8, and then third paper, actually that L is not me. So Karabashi and Lin improved it to 5/3, which is a nice number. Okay. So this is the state of art. And then for the exact algorithm, for unweighted graphs, we gave n to the 1.58K. Okay? So this is actually nothing but 2 times omega divided by 3, where this omega is called the matrix multiplication constant. It means that matrix multiplication can be done in time n to the omega. Okay, so omega so is at most 3, and then current best omega is 2.3737, so which gives us that number. And for the weighted graph, we gave a totally different algorithm that runs in time slightly better than n to the 2k, so which is n to the 1.98k. So yeah, I mean, these are our results. Okay, and then in addition to this, these are like our algorithm results. And then one like pure math question is that how, given a graph with n vertices, how many mean k cuts can a graph have? Okay, in a sense that how many different ways to partition the vertex set into k parts will minimize the number of crossing edges. So
minimum or minimum?
Minimum, yeah.
Minimum.
Okay, so yeah, we can say some lower bounds. So if you look at the complete graph, then we know that the mean k cut will be always k minus 1 singleton vertices, and then the rest of the graph. So here there are exactly n choose k minus 1 minimum k cuts. And then if you can do slightly better, if you look at the cycle, then whichever way you cut k edges, then you get exactly k pieces. So here, like the number of k cuts is exactly n choose k. So anyway, these are 2 examples. We'll give a lower bound, which is some function of k times n to the k. And then as I will show later, so the upper bound is given that is almost algorithmic. And then it is some function of k times n to the 2k minus 2. Okay? So they are tight when k is 2, but they are not tight when k is at least 3. And then we are again interested in the coefficient of k in the exponent of n. So currently it can be 1 or it can be 2. Okay. So and then yeah, our results on this space is again similar to our running time for the weighted case. So we also proved that for large enough constant k, the number of minimum k cuts is at most n to the 1.98k. So today I'm going to briefly sketch ideas for those 2 algorithms. And then let me first proceed to the FPT approximation. Okay, so this is our, so current best ratio is 5/3, but all these work are like based on the same kind of framework and ideas. So today I'm going to briefly sketch how we can barely beat 2 approximation. Say 1.999 approximation. Okay. So the main idea for this algorithm is very simple. Okay. So I'm going to show you the 2 approximation algorithm, which was known before, and then this algorithm is totally obvious algorithm. It's a greedy algorithm. And then so what we know is if greedy is already better than 2 approximation, then we're done. Okay. Then we kind of look at instances where greedy algorithm is actually gives you 2 approximation. Greedy algorithm is really bad. Then we are going to see that these bad examples will share some common structure. And then we're going to exploit this structure via another algorithm, okay? Which is very straightforward way to achieve an algorithm. Okay, so yeah, let me first introduce this greedy algorithm. Okay, so this algorithm is very easy. So for k minus 1 iterations, start from the whole graph. And then in each iteration, so we're going to greedily take the global min cut. By which I mean that in the first iteration, we first compute the global min cut of the graph, and then we get 2 pieces. And then in the second iteration, we compute the global min cut in each connected component, and then take the minimum cut. Then we get 3 connected components. Okay, so we do this k minus 1 times, and then we're gonna get 3 k connected components. Okay, so this is our algorithm, very simple. And then let's try to prove it. Okay. So yeah, one notation. Let's say that S star. Which is the partition of V into k parts. So each Si star is some subset of V. And then S star forms a k partition of the V. It's an optimal solution. And then using this partial S notation, I mean the set of edges crossing S. So and then so this is the optimal solution. And then without loss of generality, let's assume that partial S1 star is the smallest, and then partial Sk star is the largest. So and then we can we see that the size of optimal solution is exactly sum of the boundaries divided by 2 because each edge is counted twice. Okay. So given this notation, let's try to see the proof. Okay. So in the first iteration, what we know is that in the whole graph, so cutting all the edges in boundary of S1 star was a possible global min cut, and then in the first iteration, I said we're going to take the global min cut. Okay, so if C1 denotes the set of edges we delete in the first iteration, then we know the size of C1 is at most size of the boundary of S1 star. Okay, that's easy. Okay, suppose that we drew this cut, which is kind of different from S1 star, and then it's slightly more confusing in the second iteration, but I'm going to claim that even in the second iteration, either boundary of S1 star or boundary of S2 star is a possible cut that increases the number of connected components by 1. Okay? Because let's look at this stage. If you look at the boundary of S1 star, if at least one of these edges remain in the current graph, then we know that if we delete the boundary of S1 star, then we know that it's going to increase the number of connected components by 1. If this doesn't happen, then it means that all the edges in partial S1 star were previously deleted, which actually means that C1 was equal to S1 star. In that case, we can see that deleting this part will create another component. So this is any question or any more clarification? Everybody happy? Or another way to say this. Another way to see this is that right before we make the ith cut, so then we have this is our suppose that we are in third iteration, so we have 3 connected components, and then let's look at the optimal solution. Okay, so suppose that this guy is a S1 star, and then this guy is S2 star, and then S3 star, and sorry, what am I doing? Let's just ignore this. But
here, the question is, C1 in the picture, C1 doesn't cross S1 or S2.
Yeah.
But is it guaranteed, or is it and the second line you said C2, the order of C2 is less than or equal to the order of S1. If C1 doesn't intersect if they don't cross at all, then we could have taken just S1 star. It was a valid cut. Okay. So then in that case C2 is at most the partial S1 star. Mm-hmm. So when you say that or that is a possible cut, that means after cutting C1. Yeah, after cutting C1, yeah. So after cutting C1, we have 2 connected components, but we need another set of edges whose deletion will yield 1 more connected component. Okay. Yes, yeah. Oh, okay. I remember what I wanted to say here, but I think okay. Okay, so I'm going to proceed. Okay. So anyway, we know that C2 is at most the boundary of S2 star, and then we can kind of proceed in this way. So it's not hard to see. For general I, Ci is at most partial Si star. Okay. Then our algorithm, we can easily say that our cost is at most 2 times 1 minus 1 over k times opt. Okay. So this gives a 2 approximation algorithm. Okay, so I don't know why these guys are here. Okay, so there are some tight examples. Okay, so one tight example is this guy. Okay, So there are like 16 vertices, and then weight of blue edges are 2, then the weight of red edges are 1, okay? And then k is 8. So ideally, the optimal solution is to delete all the red edges, then we're going to pay 8, and then we're going to get 8 connected components. But if we just do greedy and then break ties poorly, then we're going to delete 1 blue edge, which is cost 2, and then like we're going to delete 7 blue edges, which will cost us like 14. Okay, so 8 versus 14 is almost like 2. And then another like example is just like some combination of cliques. I'm not going to go into math, but yeah, just some simple examples based on clique. So yeah, so that was like 2 approximation algorithm. And then let's try to improve it. Okay? So recall that, yeah, the proof proceeded by showing Ci is at most partial Si star. And then I'm going to be more ambitious. And then I'm going to say, okay, is there any way where we can compare Ci to partial S1 star? Okay, because like S1 is smallest, so we are like being really ambitious. So yeah, let's go back to our greedy algorithm, and then look at the first I, such that Ci becomes strictly greater than partial S1 star. Okay, so this kind of relates to like the proof of greedy algorithm. Okay. So this means is that if you look at the edges in partial S1 star, none of them is in the current graph anymore. Okay, so all these boundary edges were cut. Otherwise, like cutting edges in partial S1 star would have decreased the number of connected components by 1. Okay. So the fact that Ci is strictly greater than partial S1 star means that these edges are completely cut. Okay. So I mean S1 star can be further subpartitioned, but it means that if you look at the current graph, so these blue lines indicate the current graph. So it means that if we look at the current connected components, then some union will be exactly equal to S1 star. So yeah, this is very good for us because then actually we will know like one optimal component correctly if we guess correctly. Okay? So of course, like guessing is like very like stupid thing, but anyway, everything is a function of k. Okay? So at each point of the algorithm will kind of assume that this happened because like we don't even know S1 star or even size of it. So at each point, algorithm will assume that this happened, and then it's gonna try every possible union of its current components as S1 star, and then try to solve the problem recursively. Okay? So it's like very stupid idea, but anyway, like the branching factor for each iteration is 2 to the k because we are like taking union of subsets, and then if we do this, then we kind of guess that we guessed one connected component. So like k is decreased by 1. So if we pay 2 to the k square running time multiplicatively, then we can kind of assume that, so when we run greedy algorithm, Ci is at most partial S1 star for every Ci. So yeah, this was our first crucial idea. So then actually this idea, so this assumption gives us a very nice curve. Okay? So in this picture, so the black horizontal line indicates the size of a partial S1 star. Okay? And then we kind of saw that, yes, and then blue curve indicates the size of Ci. So we kind of assume that the blue curve is always below this horizontal line. And then by definition, the red curve, which indicates the partial Si star, is always above the horizontal line. So red curve is always above the blue curve. And then again, yeah, and then we can easily see two approximation algorithm because opt is the area under the red curve divided by 2. And then what we are paying is exactly the area under the blue curve. Okay. So yeah, so how do we, but in this picture, like so the blue curve and the red curve are far apart. So I'm gonna, then what we can see is that if the area under red curve is a constant times larger than area under the blue curve, then we know that we already like are doing better than two approximation. Okay. So in this picture, we are clearly like doing better than two approximation. Okay. But how do we like formalize that we kind of won? Okay. I do only like two very simple like certificates. Okay. So if we let A be the first index such that Ci is greater than 1 minus epsilon times the partial S1 star, which is just the blue rectangle. Okay. So the height of this rectangle is epsilon. And then if we know that A is omega of k, say like 0.1 k, then we kind of certified that there's the area of this blue rectangle is non-trivial. And then the blue rectangle is always between red curve and blue curve. So we already beat two approximation in this case, if a blue rectangle is large. Okay. So we are doing the same thing here. So let's say B is the first index, such that partial Si star is greater than 1 plus epsilon times partial S1 star. If this happens, if B is kind of far from K, then we also see that the area of a red rectangle is kind of non-trivial. And then this kind of certifies that there's a gap between red curve and blue curve. Okay. So yeah, if this happens, then we already wins. So we can assume that A is a very small, and then B is a very large. B is very close to K. Okay. So for simplicity, let me assume that A is 1, and then B is K minus 1. Okay. So yeah, then actually picture looks like this. So then we know that C1 is very close to partial S1 star, and then partial S1 star is equal to partial Si star for every component in the optimal solution, perhaps except one guy. So that's the special case we are going to consider. Okay. So yeah, now we have this like nice property of the optimal solution. Okay. So let's try to look at this. So let's consider a set of all 1 plus epsilon near min-cuts in G. So third idea is that if these are two near min-cuts cross, then what we know is that if you look at the minimum four-cut, then its size is at most 2 times 1 plus epsilon times the min-cut, okay? Because we delete edges belonging to two near min-cuts, and then we get like 4 connected components. So if we greedily take min four-cuts, then we know that if like there are 2 of them cross, then we pay 2 times the min-cut, and then the number of connected components is increased by 3. So you get 3 new components. Okay. So if we can do this like iteratively, many times, then basically what you're doing is that we're gonna pay 2 over 3 times the min-cut, and then we get like 1 new component. Okay. So if you can do this many times, then again we are beating two approximation. Okay. So let's even assume that this doesn't happen. So yeah, so near min-cuts do not cross. So they form a laminar family. Okay, so yeah, so this is our illustration of the opt. Okay, so everything except one guy is a near min-cut. And then, but there are like other near min-cuts as well. Okay, so they are like hidden here. But one good thing about the laminar family is that then actually we can represent it as a tree. Okay, so by representing a tree means that for every near min-cut, there exists tree edge such that the min-cut, the near min-cut in the original graph corresponds to the cutting that edge in the tree. Is that clear? Okay. Okay. So yeah, so it can be represented by a tree T. Okay. So then still we have this promise that all but one component is a near min-cut. So it kind of corresponds that optimal cut is corresponding to deleting k minus 1 incomparable edges in this tree. So here I assume that we root the tree at a vertex that corresponds to the last part. And then by incomparable, I mean that no edge is an ancestor of another. So this is like very strong structure at this point. And then idea 4 was this like special algorithm for this laminar curve problem. Okay, so basically, yeah, we're gonna give G and T, and then the only cuts we're gonna consider is cuts that arise by deleting k minus 1 incompatible edges in tree. Okay, so yeah, this was the algorithm, and then I had some size, but I will stop at this point. Okay, so this, yeah, so one idea is that, yeah, this algorithm was based on dynamic programming, but I'm not gonna go into details about this. Okay. So yeah, to recap this part, so I sketched the brief ideas behind the better than total approximation algorithm. And the main idea was to ensure that we haven't found a min cut, else we win. And then we really find either min cut or like min 4-wise cut. And then if many of them are small, then we win. Else instance has the most near min cuts being non-crossing. And then like we're gonna finally use a special algorithm for like very structured problem. So this was the idea behind this algorithm. And then if you optimize several things, then actually we can get 5/3 approximation algorithm, which is exactly based on this framework. Okay. So this was the first part. Okay. So some more slides. Okay. So now let me go to the second part of the talk, which is about the number of minimum k-cuts. Okay. So as I said, the previous work said that number of minimum k-cuts is at most n to the 2k minus 2. So this was done by Carter-Stein, who gave a randomized algorithm with similar running time. And then Thorob in 2008 gave a deterministic algorithm with the same running time. And then especially Carter-Stein is like very simple. I'm going to show you the full proof. It's like it's called like textbook algorithm in the computer science literature. And then again, yeah, as I said, this is bound is tight when k is 2, but it's not for when k is 3. Okay. So and then as far as I see, these two results, Carter-Stein and Thorob, are based on completely two different proofs. And then in our proof, we're gonna actually use both of them. Okay. So let me actually state the Carter-Stein proof or algorithms. Okay. So it's a randomized algorithm, and I'm going to assume that the graph was unweighted. Okay. So this algorithm consists of like one process, and then algorithm will run this same process repeatedly many times. Okay. So let me start let me introduce one process. Okay. So in the beginning of the process, we're going to start from the original graph G, and then we're going to run this while loop. So while loop says that while the current graph has strictly more than 2k vertices, then we're going to sample like random edge, and then just contract it. Okay? So this contraction may create parallel edges, and then we're going to keep them as a parallel edges. Okay? So after the while loop, then we have 2k vertices. I mean the graph with 2k vertices, and then if we unfold the contracted edges, then it means that in the original graph, we have a 2k partition, the partition of V into 2k sets. Okay, and then at this point, we anyway wanted to output k cut. Okay, so we output a random k partition formed by combining 2k sets. Okay, I'm not gonna define how we do this, because like in whatever we do it, the probability will be changed by some factor depending only on k, which I'm gonna hide. So and then this was one process, and then we're gonna just like run it that many times. Okay. So this is a entire algorithm. Okay, so this is an illustration. So in one process, we're gonna choose an edge, contract it, choose another edge, contract it. So since k is 2, and then now we have 4 vertices, and then so we're gonna choose and then we wanna like partition this like 4 vertices into like 2 sets. So there are many ways to do it, but let's say that we chose this guy, and then in the original graph, this will correspond to this cut. Okay. So is the description clear?
Algorithm clear?
Why do you have to repeat this process? The
Uh,
process already gives you some partition.
Yeah, I mean, actually, I mean, for the number of bounds, then yeah, for the number of k-cuts, then actually, yeah, we don't need to repeat it. But if you repeat it that many times, the algorithm will guarantee that it's gonna output every mean k-cut. For the proof, yeah, we just like we'll see we'll see the proof for that. For the proof, it suffices to analyze the success probability over one process. Yeah, let's go to the proof. Okay, so yeah, let's look at this graph, and then we see that the optimal cut is cutting this like singleton guy V. So again, let's say S star is an optimal k cut. Okay. And then E of S star, I'll say that there are like edges crossing S star. Okay. So let's fix like one particular optimal k cut S star, and then we're gonna study the probability that we output S star in one process. Okay. So yeah, process will contract many edges, and then I'm gonna set process became bad if it contracts edge UV that crosses S star. Because like yeah, if we contract this like crossing edge, then we know that it's never gonna output S star. So then let's let G be the current graph. Okay, so G has a V vertices, and then suppose that we aren't bad yet. The process isn't bad yet. Okay, then one thing you can easily see is that then S star is still an optimal k cut of the current graph, and then claim is a very simple claim is that the number of edges crossing S star is at most the number of edges in the current graph multiplied by this factor 2k minus 1 divided by V. Okay? And then proof is really simple. This is just the entire proof. Okay? So I'm going to consider like random k-cut formed by k minus 1 singleton vertices and the rest. Then if you look at the one edge, then probability that this edge belongs to this random choice of k-cut is at most 2 times k minus 1 divided by V, because of the probability that one vertex belongs to this k minus 1 singleton guys is exactly like k minus 1 divided by V. Okay. I mean, yeah, when k is 2, yeah, it's just like say that mean cut is at most the average degree. So this is a proof. Yeah, this is a claim. And then given this claim, okay, so then actually, yeah, we can compute the probability that we are good even after the end of the while loop. Okay. Yeah, so which is like 1 minus the failure probability. Okay. So yeah, which is so probably is this, and then if you look at the final line, then it's a bunch of fractions, and then we can see that both denominators and the numerators are decreasing exactly by 1 if you go like term by terms, and then numerator is always 2k minus 2 bigger than the denominator is 2k minus 2 bigger than the numerator. So there is a massive cancellation go on. Okay. So if you cancel everything, then it's going to be exactly the denominator will be the first 2k minus 2 terms, which is this, and then the numerator will be the last 2k minus 2 terms. Okay. So this is a success probability. I mean, this is a probability that we are good even after like end of while loop. Okay. So which is some function of k times n to the minus 2k minus 2. Okay. And then if you are good after the while loop, then we already have a 2k partition, and then we're going to randomly combine them back to the k partition. But anyway, it's like some function of k. So yeah, so what we showed is that the probability that one process outputs S star is greater than some function of k times n to the minus 2k minus 2. Okay? But this whole analysis was done for like one specific choice of S star. Okay? The only thing I assumed is it's a optimal k cut. Okay? So yeah, so then we can just go over like every optimal k cut. Since the sum of probability is at most 1, so we can see that there are at most f of k times n to the 2k minus 2 mean k cuts. Okay, so that's the proof. And then if you're an algorithm, then you can repeat this process
that many times, perhaps multiply by some log factors, and then we're going to get all mean k-cuts with high probability. Okay. So this was a sleek proof. So and then I'm going to use later some variant of Carter-Stein. Okay. So let's say that alpha is greater than 1. Okay. So let me define this m to be opt divided by 2k minus 2. Okay. So if k is 2, then it's opt divided by 2. Okay. So then actually the same kind of proof strategy will show us that if you are asking how many sets will satisfy that the boundary of boundary is at most alpha times m, then like same proof will show that there are like at most some function of k times n to the alpha of them. Okay. So I think if k is 2, then it says that number of beta and their mean cut is at most n to the 2 times beta. Okay, so we're going to use this fact later. Okay. So, but now I'm going to introduce like Thorop's theorem, which is like totally different from what Carter-Stein did. Okay. So theorem is kind of long, but let me try to read it. So this theorem says that given a graph G, we can efficiently compute n square like spanning trees of this graph, such that for every mean k cut S star, there is a tree T in from those n square collections, such that S star cuts T in at most 2k minus 2 edges. Okay, so this was the main theorem. I'm not going to show the proof, but we also use it as a black box. It was it kind of uses LP duality, and then actually all the point of his paper was to make the algorithm deterministic. So he kind of introduced a deterministic sampling of this like n squared spanning trees. But anyway, so this is a statement, and then given the statement, we can like the algorithm is very easy. So what you can do is that we go over like each tree T, and then we consider like cutting these T edges, T in 2k minus 2 edges. So we consider all ways to cut T in 2k minus 2 edges. If we do this, then we're going to get 2k minus 1 connected components. And then we're going to consider all ways to get k partitions by combining this like 2k minus 1 connected components. Okay. Then we know that, at least like then we know that every minimum k cut will be considered by these possibilities. Okay. So since for example, if this is our graph, and then these like thick edges indicate the tree edges. So if you assume that we deleted these like 2 dashed edges, then we get like 3 connected components of the graph, and then there are like 3 ways to make 2 components out of these like 3 connected components. Okay. So in this case, so none of them is a near mean cut. I mean, none of them is a mean cut. But we know that if this is a mean cut, and then if you delete these 2 tree edges, then we're going to get the mean cut. Okay, so this was the idea. So given the theorem as a black box, then there's an easy n to the 2k algorithm to enumerate all k cuts. I mean, which also gives us the bounds of the number of k cuts. Okay, so I'm going to introduce like idea how we improve this like Thorop's algorithm. Okay, let me not show the whole details, but what I'm going to sketch is that if we fix a tree T, and then if we are interested in number of minimum k cuts that cross T in 2k minus 2 edges, then one like easy answer, how many of them? Okay. So one easy answer is just like f of k times n to the 2k minus 2, which is actually like number of all k cuts, not even min k cuts. Okay. So today I'm going to show like some ideas behind slight improvement by a factor of n to the epsilon. Okay. So this is this like totally it's not stupid, but a useful reinterpretation of Thorop. Okay. So what we did previously is that we somehow were thinking about like cutting this edge in 2k minus 2 edges. cutting t into k minus 2 edges, and then assembling them back to k connected components. But what I'm doing here is that let me only guess like first component of the optimal solution. Okay, so here I denotes the number of tree edges crossing that connected component in the opt that we are trying to guess. Okay? So then what it means is that so we consider all ways to cut tree first in I edges. Okay? Then we get some connected components, and then we try every possible union to obtain just like one component, which we hope to be belong to opt. So this is what we did. Okay. This is actually the same thing as a Thorpe's algorithm, but in this way, if you look at the running time, then the running time is summation of I, some function of k times it's n to the I, because we are like guessing I edges to delete, and then if we guess I edges to delete, then suppose that we guess the one component of the optimal solution. Now we have to now we are left with k minus 1 cut problem and some forest, not tree, because we already deleted like I edges. But the number of edges in the forest is 2k minus 2 minus I. So now the promise is that so the remaining k minus 1 cut will cross the forest in at most 2k minus 2 minus I edges. So anyway, so the running time will remain the same. Okay? It will be worse by some factor depending only on k, but it's fine. Okay, so this is one stupid way to reinterpret Thorpe's algorithm. Okay. Okay, for example, if I is 1, then you can somehow guess that this is one connected component of opt, and then proceed with the rest of graph. So this was one interpretation. So main idea was like let's just like first guess one connected component of optimal solution. Okay, and then now let me throw like completely bizarre idea. Okay, I don't know. It's not clear why it's correct, but let me define AI to be the set of family of S, such that boundary of S is at most I times M. So I will be some number, and then M was this quantity, opt divided by 2k minus 2. So it's like it's same as before. So for every I from 1 to 2k minus 1, 2k minus 2, we're going to consider like S, but the only difference is that choice of S. Okay? So instead of S formed by cutting tree in I edges and recombining them, somehow I'm going to arbitrarily will try S belonging to this like set AI. And then AI has to cut T in at least I edges. Okay? And then we're going to guess S as a part of the optimal solution and then proceed. Okay? So the only difference from before was this like choice of S, which is like totally arbitrary. Okay? But anyway, like we know that the running time is still right, because we cut tree in I edges, and then by this variant of Carter-Stein, we already proved that the size of AI is at most n to the I. So the upshot is that we kind of paid n to the I, and then decreased the number of tree edges by I. Okay. So the running time is still kosher. But it's like, but as I said, it's like totally arbitrary. Why should it output all min k cuts that cut T to k minus 2 edges? Okay. So let's try to see. So claim is that let star be a minimum k cut. Then there exists ij, like optimal the optimal component sj, such that sj belongs to ai for some I, and then it also cuts t and in at least I edges. Okay. Then actually you are good, because for that sj we're going to pay n to the I to find sj, and then we decrease the number of edges by I. Okay? So this was the claim, and then actually the proof is really quite easy. Okay? So yeah, by definition of M, we know that the summation of boundaries with respect to G is exactly 4 times k minus 1 times M. And then if you look at the tree edges, the sum of the boundary edges is exactly the number of tree edges cut by this optimal k-cut, which was promised to be at most 4k minus 1. Okay? So then, yeah, by just averaging argument, we know that there exists Sj such that this holds. Okay? And then this Sj is a good optimal component. So this was the claim. But still, so far we didn't get anything. Okay. So let's try to see where we can improve. Okay. So yeah, we are gonna be happy if we find J such that this normalized boundary of Sj with respect to G is much slightly less, but strictly less than the tree edges. But yeah, let's look at the previous proof. Okay. But if you just look at the numbers, but then there's a case where we can't get anything. Okay. So if every Sj has a boundary, G boundary, exactly equal to that number, and then also the same for the tree edges, then we are not getting anything. So there is no Sj which buys us something. And in this case, we know that then all Sj should belong to A4. Okay. So, for example, if size of A4 was n to the 4, then we are not really getting anything because to decrease tree edges by 4, we need to enumerate n to the 4 sets. Okay. But the question is can A4 be really that big? Okay. So here comes our better extremal bounds in some sense. So yeah, recall that AI was defined like this, and then the previous bound we got from Carter-Stein only ensure that AI is at most n to the I. But new theorem says for large enough constant k, if basically A3 is size of A3 is at most n. Okay, I use 2.99 instead of 3 because some other there's some technicality there. So but the size of A4 was at most n to 2.75 and so on. Okay, so yeah, one important fact is that so the size of AI, at least for these 3 sets, is significantly less than n to the I. Okay, so this is something that buys us. Okay, so let me try to sketch a proof of the first item. Okay, first item is quite easy. So what we know is that if size of A was a 2n, okay, greater than 2n, then we know that there exists 2 sets that cross, which means that if you draw the Bernoulli diagram with these 2 sets, then all 4 cells are non-empty. Okay. In that case, then it's kind of similar to the previous algorithm, approximation algorithm. In that case, if you delete the boundary of S and boundary T, then we pay at most 6 M edges, and then we get 3 new connected components. Okay. So this was when A is greater than 2n. But we can easily say that if A is greater than, say, 2 to the k times n, then we can actually do this process k over 3 times. Then it means that we're going to get k connected components. And then we are paying slightly less than opt by the choice of parameters. Okay. So it kind of gives us contradiction because we found the k cut, which is strictly cheaper than the opt. Okay, so this was the proof idea. And then one thing I wanted to mention is that, so this claim, it's a trivial claim, but it says that, so another way to state this is that for a set system with strictly more than 2n sets, it's a dual VC dimension. So usual VC dimension of the dual set system is at least 2. Okay. Yeah, because the other items will use better improved bounds for like 3 and 4 instead of 2. Okay. So yeah. So this is our weapon, and then yeah, and then this is what we do. So now we change the definition of AI, okay? Because we have a better extremal bounds, and then we adjust parameters since we are getting something for like small values of I when I is a 2, 3, 4. Then actually we will get some non-trivial improvements over the just naively enumerating all the 3 edges. Okay, so this was a proof. Yeah. Okay. So general cases are more tricky because here like we only shape the n to the epsilon in one place, but my goal was to save n to the epsilon in like k places. Okay. So yeah, so it's we had to do it like we had to gain this thing k times. Okay, so we kind of did it by carefully designing potential function and then so on. Okay. And then again, as I said, we got improved bounds on sets with dual VC dimension 3, which actually, I mean, so dual VC dimension 2 was like very well-known fact. It was like, yeah, just like if you have more than linear sets, then 2 sets cross. But yeah, somehow we kind of improved this bound, but our bound is not tight. Okay, so this is a conjecture. Actually, it's like just totally independent, crisp conjecture. So I want to say that if you look at any set system that has say like 100 times n cube sets, then there exists like 3 sets A, B, C, such that if you look at if you draw the Bernoulli diagram, then all 8 sets, all 8 cells of their like Venn diagram, sorry, not Bernoulli, Venn diagram, is not empty. Okay. In other words, they're like dual VC dimension is at least 3. I think, yeah, must have been known. Yeah, already we couldn't find the proof, so I think getting n to the 4 was a kind of, yeah, it's not trivial, but like was doable in some elementary way. Bound we got was n to the 3.75.
So the set system on n elements.
Yeah, n elements, yes. And then yeah, those 2 sets can be the same and so on. Yeah.
N to the 31. So
yeah, our bound. Yeah, so our current bound gives us n to the 3.75. And then proof was like kind of like non-trivial. I think n to the 4, yeah, could be doable, yeah, in elementary, but like our proof for like n to the even 3.75 was a non-trivial. And then I think that n to the, yeah, so, but it can't be like better than n to the 3, because if you look at all the triples, then we have n to the n choose 3 sets, but we can't take 3 sets that have that satisfy this condition. So yeah, n choose 3 is a lower bound. I can't even conjecture that n choose 3 is a right bound, but yeah, I'm going to refine it.
N to the d.
Sorry?
You conjecture n to the d and replace 3 by d.
Actually, yeah.
I mean, that would be natural, right?
Yeah.
Oh, so instead of 3 sets.
But but when like it was 2, then actually the correct was 1. So I don't know how it. So like if you look at the VC dimension, then it's like actually d becomes n to the d becomes like d, and then actually there's like some relationship between the dual VC dimension and the VC dimension. But I think there was like some exponential or like log factor involved, and then that just bound itself is kind of weak. And then yeah. So this is one nice open problem, or like not open problem, that we couldn't find. By the way, one thing I also should have mentioned is that even if actually our bound was like 1.98 from 2. And then even if we get the optimal thing, it's perhaps we get like 1.95 or something. Yeah, so all the loss was actually coming from this like potential business. But anyway, yeah, actually it's a nice problem. Okay, so again, yeah, this was a recap of my results. So we got better approximation algorithms, and then better like exact algorithms, and improve the external bounds. So yeah, if you look at the hardness, lower bound, then at least like they are like n to the k, essentially coming from the k-click. Actually, and then if you look at the even the approximation problems, actually they are like in some sense all like coming from finding hardness or finding k-click. So it's kind of very interesting to see whether actually k-cut is like k-cut looks much more like much harder problem than finding k-click, but actually perhaps finding k-cut will be done in the same complexity as finding k-click. We don't have any like better lower bounds. So that's it. Okay, thanks.